Hello everyone, myself Kamna Singh, Assistant Professor in Computer Science and Engineering Department in Ajay Kumar Garg Engineering College, Ghaziabad. Today we are going to discuss the topic Arithmetic Circuit. This particular topic is taken from Computer Organization and Architecture subject. Today we are going to discuss some topic related to arithmetic circuit. That is, first we are going to discuss the topic arithmetic microoperation, then next adder-subtractor, incrementer. After that we are going to discuss arithmetic circuit, and then after we are going to discuss the arithmetic logic unit. What is arithmetic microoperation? Actually, microoperations are the operations when any operations performed in the register is called as a microoperations. And arithmetic microoperation is addition, subtraction, increment, shift of microoperations. There are so many arithmetic operations are there. Also, some additional microoperations are there, that is the add with the carry or subtract with the borrow or a transfer. These are the some arithmetic microoperations. These are the some examples of the arithmetic microoperations. There are addition, subtraction, increment, decrement or transfer. These are the some. Here we are taking the R1 register and R2 register, and the resultant will be stored in the R3. R1 and R2 we are considering as a 4-bit register. You can take any size of the register, maybe 16-bit or a 32-bit, whatever the size we are taking. In this particular example, I am taking the 4-bit register, so that just if there is an additional register R1 plus R2, here suppose that the R1 equal to 1010 and R2 is whatever the binary sequence, that is here I am taking 0101. So when we are going to conclude the R1 plus R2 and the stored with the R3 register, simply we are going to add 0 plus 1 and then LSB to LSB, and next 1 and 0 and then 0 and 1 and 1 0, so that we can conclude the resultant, and this particular result will be stored in the registered R3. These are the simple operation, that is the content of the R1 and the content of the R2 will be added, and this particular resultant will be transferred to the R3 as a resultant register. Now, the second micro operation is R3 of R1 minus R2. R1 minus R2 means here again I am taking the R1 and R2 are the size of 4-bit. So, R1 is considering as a R1 and minus R2, that is content of the R1 is subtracted by the content of the R2, and the resultant will be stored in the R3 register. When we are going to take the R3 is to R1 minus R2, actually we are going to apply the 2's complement subtraction, that is R1 plus 2's complement of R2 we can say, and let R1 equal to 0101 and R2 equal to 1101, suppose, then R2 complement is what? R2 complement means this is the 1's complement. Here I am taking R2 is 1101, so the R2 complement is what? 0010, and the R2 complement plus 1 is considering as a 2's complement. So we can use this R2 complement plus 1 is as a 0011 will be there. So when we are going to subtract operation, then R1 minus R2, it means R1, or you can say the first register value is as it is, and the second register value is 2's complement value will be considered. So here in this particular example, we are going to take that R1 minus R2 is what? 0010, and the R2 is what? R2 minus R2 means the complement of R2, the complement or 2's complement of R2, that is 0011, and the resultant, this 0101 will be stored in the R3 register. The next is the R2 complement. In the complement, we are considering is as a 1's complement. 1's complement means the binary sequence of 0 and 1 will be revert back, that is a 1 will be converted into the 0 and 0 will be converted into the 1, that is the 1's complement. So here I am taking the example of the again the 4-bit register, that is R2, and R2 is what? 1010 is there, and the R2 complement is what? The 1 will be converted into the 0 and the 0 will be converted as a 1. In the third operation, there is a 2's complement, or you can say the negate operation. How we are concluding it? The same procedure will be followed as we are doing in the R1 minus R2. So R2 plus R2 complement plus 1 means first we are taking the 1's complement of the content of the R2, then add plus 1. Here the R2 we are considering as a 100. It means there is a 4-bit R2 register, and the R2 complement means the 1 value is considering as a 1's complement, that is 0, and 000 is considering as a 111. So R2 complement plus 1 is what? R2 complement plus 1 is directly as a plus 1, but here 1 is the 1 bit and R2 register is a 4 bit. So 1 value will be considered as a 4-bit number. So we can write here as a 1 as 0001, and after that these particular 2 values will be adding, and the resultant will be stored in the R2 register as a 2's complement of R2. The next is the R3, that is R1 minus R2 you can say, or the R1 plus R2 complement plus 1. Both are the same thing, or you can say that is a subtraction or the R1 plus 2's complement of R2. So here I am taking the example R1. Again R1 and R2 both are the 4-bit register, and R1 is suppose 0011 and R2 is 1011. So R2 complement is what? The second value, the second content, or you can say the second register value will be treated as a 2's complement, so that the R1 minus R2 will be performed. So R2 complement is what? That is a 1's complement. That 0 is converted into the 1 and 1 is converted into the 0. So R2 complement plus 1 is here, that is 0101. So the R3 is what? R3 is R1 plus R2 complement plus 1, that is 0101, and R1 is 0011. So here I am writing here 0011 is there and 0101 is there. So the resultant will be taken as 1000. That will be stored in the R3 register. Now the next micro operation is R1 plus 1. Here we are going to increment the register R1. So R1 register is a 4-bit register, and we are taking that whatever the value, or you can say that is the binary sequence. So 0100 is there, R1, but the 1 is what? 1 is the 1-bit value. So this particular 1 will be considered as a 4-bit number. So that's why here I am writing here that is a 0001. So 0101 is there, and now R1 equal to 0101. The next is the decrement. Decrement is again the same thing, just like the R1 minus R2. But here, because the decrement operation is there, the second value is 1. The second value is 1 means here I am taking the R1 as a 4-bit number. So 1 should be considered as a 4-bit number. So R1 plus second values 2's complement will be added to the R1 register. So second value is what? Here in this time that is 1, or when we are doing the R1 minus R2, at that moment R2 is the second variable. Here minus 1 means 1 is the second variable. So 1 will be considered as a 4-bit value, again taking the 2's complement and then adding this particular content of this particular register to the R1. So R1 plus 2's complement of 1 which means what? R1 is here plus 2's complement of 0001 is there. This 0001 complement, that is the 1's complement, will be considered. 0 is converted into the 1 and 1 is converted into the 0, and then this value will be added plus 1. So the resultant will be what? That is 41. So R1 minus 1 actually we are doing in the content of R1 plus 4 1s are there. That will be as a decrement operation, R1 minus 1. Now, with these particular examples of the arithmetic micro operation, we can create a circuit. When the n-bit binary adder we are going to make, suppose that this is the 4-bit binary adder. If the 4-bit binary adder means what? The first value, or A plus B, we are going to add A plus B. Here A is the 4-bit number. That is the sequence of binary sequence, that is a 0101, whatever the sequence is there, but it is of the 4-bit value, and the B is again the 4-bit value. So as a generalized format, we can consider as A is A0, A1, A2 and A3, and B is the B0, B1, B2, B3. And then next is when we are going to add these particular LSB, means A0 and B0 is the LSB. We are going to add, there is a SNOT, and then A1 and B1 will be added, S1 will be there. Then at that moment, may be possible there will be a carry will be generated. In this particular time, the carry will be also added with the next third values, that is a A2, B2 plus that particular previous carries, and the resultant will be applied as a S2. Here you can see that there is a C1, C2, C3. These are the carry forwarded from first input to the next input. So, in the n-bit binary adder, simply we are taking the A0, A1, A2 with the addition, because the addition is there, that's why we are taking that is here as a full adder. In this time, the carry value is 0, C0 equal to 0, because at that when the LSB is taking A0, B0, in this particular time, the carry will not be generated. So, that's why here at that moment, at the initial time, C0 is 0. After that, A0, B0 will be added and the S0 will be generated, and A1, B1 will be added and the S1 will be generated, and so on. This particular example of the n-bit binary adder. Now, if this particular circuit is only for the addition purpose, if we are needing the required that particular circuit will be behaving as a adder and subtractor both. At this particular example, we are taking the n-bit adder subtractor. The both having the A and B again having the 4-bit number. So, A0, this is the 4-bit adder subtractor circuit. Here A0, A1, A2 and A3, and B0, B1, B2, B3. B0, B1, B2, B3 is the second variable. So, when we are going to add A plus B, at that moment A plus B, the B is there. When A minus B means A plus 2's complement of B. At that moment, B complement will be considered. So, that's why we are taking the M value, again the next variable, that is the M, and this particular M will be going to the XOR value, and these B and M value will be XORed and created the second output of the full adder. Carry will be forwarded like the previous one. Now, in this particular adder subtractor circuit, if we are going to consider, there is a M. M is what? M is the single bit value, means what? M having 0 or 1 value. So, in the case 1, there is a M equal to 0, and the second case there is a M equal to 1, and the B value will be XOR with this particular M. So, in the mode operation, in the first case, because B is again the 1-bit value, so may be possible B is 0 or B equal to 1. So, B equal to 0, when B equal to 0, then B XOR 0, and this particular 0 is what? That is M. B XOR 0 means B XOR M equal to what? 0 XOR 0, 0 XOR 0. Apply the operation so that the resultant will be 0. And next, when B equal to 1, then B XOR 0. B XOR 0 is nothing but XORing the M. B XOR M, that is 1 XOR 0, because in this particular case we are considering M as a 0. So, 1 XOR 0 equal to what? That is 1. Now, if we considering that, and at the starting in the case 1, we are using B equal to 0 and the resultant will be 0. And when we are using B equal to 1, the resultant will be 1. It means what? Actually, when M equal to 0, the B value will be considered as B. It means what? The circuit will be considered as A plus B. In the second case, when M equal to 1, B equal to 0. So, 0 XOR, in this particular time, B XOR 1. B value lies between 0 and 1. 0 XOR 1, that is B complement, and B XOR 1. So, 1 XOR 1 is what? 0. That is B complement. It means what? At the starting, we are considering B equal to 0, but the resultant will become as 1. That is the complement of B. And when starting, we are taking the B equal to 1, but the resultant will be considering as what? That is 0. So, B complement will be there. It means what? Actually, we are using B complement. So, in this particular time, if I am taking the C input as a 1, so that this particular circuit is considered as a subtractor. So, in this particular adder subtractor, if we are going to only adding this particular M wire or a mode wire, so that the adder circuit will be constructed as a adder subtractor circuit. Means in this particular way, when m equal to 0, so it will be considered as an adder, and when m equal to 1, then the circuit is considered as the subtractor. But again the same problem is there. In the both circuit, n-bit adder only perform the addition operation, and in the next adder subtractor, this particular circuit only perform the addition subtraction. What if we need increment, decrement or transfer or some other operations we are need? At that particular moment, we are considering the arithmetic circuit. Now, the next circuit is binary incrementer. Incrementer is what? When the a plus 1. So, we are using as a binary incrementer. In this particular example, we are taking the 4-bit binary incrementer. That's why there are 4 half adders will be considered. And here A0, A1, A2 and A3 is there. A is the 4-bit value and the 1 is written as 1 bit. It means the 1 should be as a 4-bit. That's why we are taking 0001 here. That is the 4-bit value. And now we can add A0 plus 1, A1 plus 0, A2 plus 0 and A3 plus 0. So, produces the sum value will be there. S0, S1, S2 and S3. So, in the simple binary incrementer, we can use full adder also and the half adder. So, in this particular circuit, in the 4-bit binary incrementer, we are A plus 1 addition will be there. Now, in all the circuits which we have studied, that is n-bit adder, subtractor or incrementer, both having the 1 or 2 operations only. But we need a circuit in which all the arithmetic micro operations will be performed. That's why there is a need of the arithmetic circuit. In this particular arithmetic circuit, we are using the addition, subtraction, increment, decrement, transfer, all the operations performed as a arithmetic operation will be in a single circuit. Before starting the arithmetic circuit, we have to analyze all the operations. When we are analyzing all the operations, so that we came to know which particular component or which particular circuit we have to use in the arithmetic circuit. Here, in the first operation, that is the addition operation, A plus B is here. In the A plus B, suppose that we are going to create the 4-bit arithmetic circuit. In the 4-bit arithmetic circuit, both the A and B will be the 4-bit values. The 4-bit numbers means A0, A1, A2, A3, B0, B1, B2 and B3. So, A0, A1, A2, A3 means what? Whatever the sequence, binary sequence of the value, that is 0, 1, 1, 0, whatever the binary sequence. And B will be again the binary sequence. But we can analyze that when the addition operation is going on, then A plus B is performing. There is a opcode is plus and the A and B is the 4-bit value. B is not changed. B is the second variable, that is as a considered as B. Now, in the subtraction operation, as we taking in the previous one, when we are studying the subtractor circuit, in this particular way, what? A minus B. A minus B, we can write it here as a plus 2's complement of the second variable, and here second variable is B. So, A plus 2's complement of B means what? The 1's complement plus 1. So, here written over here, that is A plus B complement plus 1. A plus B complement plus 1. Now, addition and subtraction, we can see the plus and plus means both having the opcode as a plus. But in the subtraction operation, B value will be changed. Here in the additional, there is a B, but in the subtraction, there is a B complement will be there. Again, there is a is considered as the A0, A1, A2, A3 and the B complement is considered as the B0, B1, B2, B3 complement. Now, in the third operation, increment operation. Here in the increment operation, if we are taking the 4-bit value, that is A plus 1. So, A will be A0, A1, A2 and A3 and the 1 value is 0001 because the A is already as a 4-bit. So, 1 is considered as a 0001. In a next decrement operation, that is a minus 1. Even though there is a minus sign, but when we are using the 2's complement of the second variable, so that in this particular way, we considering the minus sign converted into the plus. So there is a minus 1 can be written as a plus 2's complement of 1. A is what? 4-bit value, and the 1 is what? 1 is a 1-bit, but we can consider it as a 4-bit value. So 1 can be written as 0001, and a value is a0, a1, a2, a3, and the plus 1 means plus 1, simple values. So we are adding this 1110 plus 1, that is 4 ones. It means decrement operation will be performed when a will be added with the 4 1 values. Now, when we are analyzing all these arithmetic micro operation, we can concluded that the first thing, the first variable of a, whatever the micro operation is going to perform, the first variable, that is a, is not changed. A is just having the same content as the previous, means in the addition a value is there, subtraction is the a, increment, decrement, transfer, whatever the operation is performed, a is always same as it is. But the b value is changed. In the addition, b value is b, but the subtraction, there is it converted into the b complement. When increment operation, then the b value is changed as a 1, and when the decrement operation, b value will be changed as a b complement, and when the transfer operation, the value will be 0, b value will be changed as a 0. So we can conclude it that the a value will never change whatever the operation is performed, but the b value is changed as a b complement, 0 and 1, that is 4 values will be there. So we need a circuit which perform the 4 values and output will be generated only 1. So we can use in this particular B selection value, we can use the multiplexer. And what will be the size of the multiplexer? That is because the 4 input value, out of these 4, we can use only 1 at that moment whenever we perform the addition operation. So that only 1 B value we need. If the increment operation is there, so only 1 value, that is 1 operation we need. That's why we can use B complement having a mux with a size of 4 cross 1 multiplexer. And now the next thing is that A value will be changed, not changed, but the plus. Again, you can see, even though A minus B and A minus 1 will also be there, the operations, but we are using 2's complement. That's why the opcode in all the operation is plus. That's why for these particular purpose, we can use the full adder. And because we are using the 4-bit binary circuit, so that's why we can use, there is a 4 multiplexers and the 4 full adder circuit is there. 4 multiplexer and 4 full adder are there, and the 4 multiplexers are what? What will be the size of multiplexer? Because the B having 4 values, B complement 0 and 1, that's why there is a multiplexer size is 4 cross 1. We are not taking that 8 cross 1 because the B value having a 4 values. That's why there is a 4 cross 1 multiplexer, and because the 4 cross 1 multiplexer is there, so the selection line in the 4 cross 1 multiplexer, that is what? Log of base to k, that is log of base to 4. So the selection line, 2 selection line will be there, that is S0 and S1. Now, in the 4 cross 1 multiplexer, as we can see in this particular diagram, there is the first input of the multiplexer is considered as B, and the second input is B complement, the third input is 0, and the fourth input is considered as 1. So, in the 4 cross 1 multiplexer, there are 4 values, that is B complement, 0 and 1, and this particular multiplexer at the moment only one operation is going to perform. That's why this particular Y output is going to this particular full adder as a second value, as a B considered, and this X0 is considered as a A0 because A value is never ever changed whatever the operation is going to perform. That's why all these A0, A1, A2 and A3 will be going directly to the full adder. Now, the third value 2 and 3, this 2 and 3 we are using 0 and 1 as a B input. So at the starting 0 value are taking as an input and the 1 value is the we are using this inverter, so that this 0 will be converted as a 1 and taking as the fourth input value of the multiplexer. Now this 1 will be goes to the, this is the fourth input value of the multiplexer. There is, because there is a full adder we are using, the 4 full adders, because the 4-bit arithmetic circuit we are going to perform, that's why there is a carry value will be also there, and these carry values, carry input values will be forwarded to next, A0 to A1 to A2 and A3. And the output will be D0, D1, D2 and D3 will be considered. Now the selection line, because the 4 cross 1 multiplexer is there, so that's why the selection line will be log of base to 4, that is the 2 selection line, and these 2 selection line will be going all these multiplexer. And because there is a 2 selection line is there, it means the combination will be 4 values, that is 2 to the power 2. So you can say the 0, 0, 0, 1, 1, 0 and 1, 1 operations will be there. Now this is the truth table for the arithmetic circuit. The first is the selection line S0, S1 and C input. As we can see, there is only 2 selection lines are there. S0 and S1 is there. Means what? The combinations are what? 0, 0, 0, 1, 1, 0 and 1, 1. Only 4 values are there. But because the C input value is again the 1-bit value, and this particular 1 bit will be lies between 0 and 1. So that's why we are using this Z input as 0, 1, 0, 1, 0, 1, 0, 1. That's why these selection lines will be repeated. You can see in this particular blue box, there is a 0, 0 is repeated, then 0, 1, then 1, 0 and then 1, 1. So these values will be repeated. And now the Y is what? Y is coming from the multiplexer output, and this particular Y is coming from multiplexer output, and this multiplexer output is going to the treated as a B value, and these B value is used as a B complement 0 or 1, and because the C input value is a 2 times 0 or 1, that's why B is again repeated, that is a B complement 0, 0 and 1. Now the output is considered as D equal to A plus Y plus C input. Output is D equal to A plus Y plus C input. So this is the output of the arithmetic circuit. Now one by one we are taking the look. The first thing, in the first octet you can see there is a 0, 0, 0, 1, 1, 0 and 1, 1 is there. So there is a, in the first 0, 1 is there. A0 is considering like, and the B is what? B is in this particular time the wire B will be considered, that is a B, B0, B1, B2 and B3 will be going there. That is the add, and when the C input value is there, so 1, add with the carry, and the next value here there is the only the B complement value will be activated, as the selection line 0, 1 will be activated. So the B complement value will be activated, and first thing A plus B complement and the C input value. So the A plus B complement plus 1 value will be there. In the transfer A, there is a 1, 0 and 1, 0, 1. You can see in the selection line when the 1, 0 is there, at that moment only the 1 value of this particular value will be considered. And in the last one having the D equal to decrement and transfer of A. When the selection line is 1, 1 is there, at that moment that is A plus 2's complement of 1 is there. In this particular, again the same procedure will be followed. A, when all the 4 ones are there, it means what? Actually we are negating, or A minus 1 will be considered as. So the transfer of A is there. Here is the arithmetic logical unit. Arithmetical logical unit operation. The first thing is that in the arithmetic circuit and the logical circuit and the multiplexer. So the arithmetic logical shift unit will be considered. In this particular truth table, you can see the simply there is a arithmetic circuit operation. All these operations will be performed. Next, the logical operation will be performed, and next is the shift micro operation will be performed. Thank you.